What is wind? Wind is moving air. Although you can't see the wind itself, you can see how its force affects things in its path: leaves, grass, flags, laundry on a clothesline, even your hair on a windy day. How wind is created. Wind is simply air in motion. It is caused by the uneven heating of the Earth's surface by the sun. Because the Earth's surface is made of very different types of land and water, it absorbs the sun's heat at different rates. One example of this uneven heating can be found in the daily wind cycle. Since ancient times, people have harnessed the wind's energy. Over 5,000 years ago, the ancient Egyptians used the wind to sail ships on the Nile River. Later, people built windmills to grind wheat and other grains. The early windmills looked like paddle wheels. Centuries later, the people in Holland improved the windmill. They gave it propeller-type blades, still made with sails. Holland is famous for its windmills. In this country, the colonists used windmills to grind wheat and corn, to pump water, and to cut wood at sawmills. Today, people occasionally use windmills to grind grain and pump water, but they also use modern wind turbines to make electricity. A wind turbine is a device that converts the wind's kinetic energy into electrical energy. Wind turbines are manufactured in a wide range of vertical and horizontal axis types. The smallest turbines are used for applications such as battery charging for auxiliary power, for boats or caravans, or to power traffic warning signs. Slightly larger turbines can be used for making contributions to a domestic power supply, while selling unused power back to the utility supplier, via the electrical grid. Arrays of large turbines, known as wind farms, are becoming an increasingly important source of intermittent renewable energy and are used by many countries as part of a strategy to reduce their reliance on fossil fuels. Wind was shown to have the lowest relative greenhouse gas emissions, the least water consumption demands, and the most favorable social impacts compared to photovoltaic, hydro, geothermal, coal and gas. Let's see the main parts of the wind turbine. Blades, lifts and rotates when wind is blown over them, causing the rotor to spin. Rotor, blades and hub together form the rotor. Tower, made from tubular steel, concrete, or steel lattice, supports the structure of the turbine. Because wind speed increases with height, taller towers enable turbines to capture more energy and generate more electricity. Pitch, turns or pitches blades out of the wind to control the rotor speed, and to keep the rotor from turning in winds that are too high or too low to produce electricity. Low-speed shaft, turns a low-speed shaft at about 30 to 60 revolutions per minute. High-speed shaft, drives the generator. Gearbox, connects the low-speed shaft to the high-speed shaft and increases the rotational speeds from about 30 to 60 rotations per minute, to about 1000 to 1800 revolutions per minute. This is the rotational speed required by most generators to produce electricity. Generator, produces 60-cycle AC electricity. It is usually an off-the-shelf induction generator. Brake, stops the rotor mechanically, electrically, or hydraulically, in emergencies. Anemometer, measures the wind speed and transmits wind speed data to the controller. Controller, starts up the machine at wind speeds of about 8 to 16 miles per hour and shuts off the machine at about 55 miles per hour. Turbines do not operate at wind speeds above about 55 miles per hour because they may be damaged by the high winds. Wind vane, measures wind direction and communicates with the yaw drive to orient the turbine properly with respect to the wind. Yaw drive, orients upwind turbines to keep them facing the wind when the direction changes. Downwind turbines don't require a yaw drive because the wind manually blows the rotor away from it. Yaw motor, powers the yaw drive. How the wind turbine is working. Let's see the basic working. When the wind is blowing, the blades turns the rotor. The rotor is connected to the generator. While rotates the rotor, generator produces the electricity. Let's get deep into the functioning of each parts and how the wind energy turns into electrical energy. First we will see the wind blades, the blades having the wing profile like the airplanes. The shape of the blade what makes the wind turbines to rotate, but only if the angle of attack is right. By pitching the blade into the wind, the blade generates lift. The direction of the airflow is the combination of the wind and the airflow caused by the rotation of the rotor near the blade root. The radial velocity of the blade is low, but on the tip of the blade the radial velocity of the turbine is as high as 80 meters per second. This is why the tip of the blade twisted into the direction of the airflow. It ensures the right angle of attack, to harvest as much energy from the wind as possible. The wind turbine blades typically turns at a very low rate of RPM due to the issues of the noise and mechanical strength. At this level of rotation we cannot produce any meaningful electricity from a generator. We have to increase the speed of the rotation of the generator. So this setup used a planetary gearbox to achieve the maximum speed. If wind is blowing at high speed, turbine may damage. So the brake system is placed to control the overspeed in windy days. Electricity produced from the generator passed through a cable towards the bottom of the tower where the step-up transformer is situated. The wind turbine should face toward the wind for maximum power generation, but wind can change its direction at any time. An anemometer and wind vane is located on top of the nacelle. It measures the wind speed and direction. If any changes in the wind direction it sends to the controller. The control system controls the yawing mechanism to rotate the nacelle with the help of yaw motor, so the wind turbine can always align with the wind's direction. Velocity also changing in the blade due to the wind speed, so blade tilting mechanism is located at rotor. This is called pitch system. It tilts the blades at corresponding direction with proper alignment to ensure the velocity. To check the efficiency of the wind turbine, measure the wind speed at upstream and downstream over wind turbine. The wind speed of downstream is much smaller than the upstream. This is because the blades absorb some kinetic energy from the wind. The same amount of energy is converted as mechanical power of the wind turbine. A wind turbine absorbs 100% of the available kinetic energy, only if the downstream wind speed becomes zero. However, zero wind speed at downstream is physically impossible condition. Now let's see what is Betz' law about the wind turbine. According to Betz's law, no turbine can capture more than 1627. That is 59.3% of the kinetic energy in wind. The more kinetic energy a wind turbine pulls out of the wind, the more the wind will be slowed down as it leaves. This is called Betz's law. Let's prove the theorem. Let's assume that the average wind speed through the rotor area is the average of the undisturbed wind speed before the wind turbine, called as V1, and the wind speed after the passage through the rotor plane, called as V2, that is, V1 plus V2, divided by 2. The mass of the air streaming through the rotor during 1 second is equal to multiplication of the density of air swept area around rotor, the average wind speed through the rotor area. According to Newton's second law, the power extracted from the wind by the rotor is equal to the mass times the drop in the wind speed squared. Substituting m into this expression from the first equation we get the following expression for the power extracted from the wind. Now, let us compare our result with the total power in the undisturbed wind streaming through exactly the same area F, with no rotor blocking the wind. We call this power P0. The ratio between the power we extract from the wind and the power in the undisturbed wind is then P by P0 equals 1 by 2 into 1 minus V2 divided by V1 whole square into 1 plus V2 divided by V1. We may plot P divided P0 as a function of V2 divided by V1. We can see that the function reaches its maximum for V2 divided by V1 equals 1/3, and that the maximum value for the power extracted from the wind is 0,59 or 16/27 of the total power in the wind.